Okay. So, hi everyone. Welcome to the IARCS verification seminar series. It's a pleasure to have Krishna here with us today. Krishna is from the Department of Computer Science and Engineering at IIT Bombay, and she works in a variety of different areas which broadly come under automata, logic, games, timed and probabilistic systems. More recently, I believe she's done some work in RL with correct by construction RL and such things. Today, she'll be telling us about verification of concurrent programs under release acquire. Yeah, so over to you, Krishna.
Okay, thanks, Madhukar. And I also would like to thank the organizers for giving this opportunity. Okay, so I guess we'll get started. All right, so I would like to begin by, just motivating concurrency itself, even before we look at the actual problem. So the simple motivation for concurrency is that we have concurrent systems everywhere. So when I say everywhere, what I mean is across levels of system design. So let's start looking at, say, the lowest level of system design, which are at the level of chips. So now at this level, if we look at all the architectures by the leading manufacturers, right, like Intel or ARM or IBM, invariably they're all multi-core architectures, which means they have concurrency at that lowest level, at the level of chips. And now let's move on to the highest level of system design, let's say distributed databases. So now if we look at the databases of, let's say, Facebook or Amazon, they have what is known as this geo-replicated system. So basically, it's like they have these servers distributed across the world. So now sitting here in Mumbai, if I like the Facebook page, or if a particular post in Facebook of a friend sitting in Mumbai, somebody who sits in some other part of the world should see it consistently, right? So to maintain this consistency, that is where this geo-replication works. So essentially, this is yet another, instantiation of concurrency at a highest level of system design. But it's not just that we have concurrency, let's say, in the architecture level or the distributed databases level. Now, if you look at the modern implementation of programming languages like C++ or Java, we do have parallelism and concurrency within the programming language. So that is why, we have terms like threads, locks, release accesses, acquire accesses, and so on and so forth. So indeed, this is the starting point for today's talk, the parallelism and concurrency inside programming languages, and also in general to what are called weak memory models. So very high level definition of weak memory model is that a weak memory model provides sound semantics for high performant concurrent models. Okay, so what exactly do we mean by that? So if we look at traditionally any model for concurrency, there is this trade-off between, let's say, on one hand, easy programmability, and on the other hand, high performance. Okay, so the traditional model for concurrent systems is what is called sequential consistency, which has an interleaving semantics. Now, sequential consistency, it's very easy to program in sequential consistency, even though it suffers performance with respect to the modern hardware architectures. Now, at the other end of the spectrum, we have so-called relaxed or weak memory models, which have a very high performance on the modern architectures. However, these are barely synchronizable. So somehow, which is also the focus of today's talk, we have in between both of these, the fragment called release acquire, which is what we are going to look at today. And release acquire is a fragment of C11. So let's first ask what is C11 and then zoom into release acquire. So the C11 memory model has, let's say, two parts. On one hand, it has what are called non-atomic data accesses. So these are the traditional data accesses which are not thread safe. And the other hand, we have the atomic data accesses. Now, within the atomic data accesses, we have, again, a wide spectrum. Of course, I have not written everything. I've written what is more relevant for today. So it has the relaxed, which is highly performant and barely synchronizable relaxed kind, all the way down to sequential consistency, which is very expensive to implement, and it has high synchronization. And as we see, release acquire sits in the middle. So the nice thing about release acquire is that the performance is very good. At the same time, it also supports some interesting synchronization features like, say, message passing idiom. Another way to kind of very simply define release acquire is take the C11 memory model and let's make all the reads to be acquire reads and all the writes to be release writes and all the updates or atomic read writes to be acquire release kind. Okay, so this is release acquire in a nutshell. So to understand release acquire, and especially what I said, right, that it supports message passing, let's start by looking at some very well-known examples so that we understand how release acquire differs from the standard sequential consistency. So these are two very famous examples, store buffer and message passing. So the question is, we are going to ask whether under the store buffer example, I will talk in detail about it, whether we can reach a situation where Rx and Ry are both 0 for store buffer. And message passing, we are going to ask if the value of Rx can be equal to 0. Okay, I've written 1 here, but it's okay. You can ask equal to 0 also. So how does the store buffer look like? So I have two processes with two shared variables x and y. Initially, both x and y are 0. And the first process writes 1 into x, and then it is reading the value of y into its local variable or local register ry. And process 2 is writing 1 into y, and it is reading from the variable x into its local variable rx. So the question is it possible for us to reach rx and ry to be both 0 when we finish executing this program? So if we think in terms of sequential consistency, we know that this is not possible because let's say you start executing process 1 first, then you will write 1 into x. And the moment that happens, you cannot read 0 into Rx. Likewise, if process 2 were to execute first, you will not be able to read 0 into R1. However, as we will see, this is possible under release acquire, that it is possible to obtain both Rx and Ry to be 0. So let's see how this is possible. So notice that the first thing that is shown in process 2 is it is swapping the first and second statements.
Alert from Google, password required.
I'm so sorry. Okay. So the second process has basically swapped the read and write statements. So this was done because, first of all, they pertain to different locations, right? Or different variables, x and y. So thanks to this swapping, now when I look at an execution, I can now read 0 into Rx because 0 was the initial value. Now process 1 can write 1 into x. I can continue with by reading y 0 into ry, and finally the second process can write 1 into y. As a result of which what happens is I am indeed able to read 0 into both Rx and Ry. So a more formal explanation for this is given in terms of so-called execution graph. So what you see here is such an execution graph. So the execution graph, basically, if you look at the relations, so there is a program order which connects events from the same process or same thread. Basically in the order they appear. Now there is a reads from relation which reads to the corresponding writes. And then we have the modification order, which is basically connecting the write events as in the order they appear for every variable. Okay. So now an explanation why this is allowed under release acquire is that now if you look at the second process, if you look at the read x0 event, and if you look at the write x1 event in the first process, notice that there is no path that leads from write x1 to read x0. So somehow process 2 is unaware of the write that happened in the first process. And that is why this is a consistent execution graph under release acquire, allowing us to read 0 into both Rx and R1. Now, let's look at the second example, message passing. Now, this behavior is very different from the first example. So first of all, notice here that the second process is reading the value of x into Rx, and we are asking whether I can read 0 into Rx. So unlike the first example, here, the second process will not be able to read 0 simply because, so notice that the first process is making 2 writes. It is writing 1 into x, 2 into y. The second process is basically waiting, right? It's in a loop. It's waiting just enough time so that the value of y is going to change from 0 to 2. And the moment that happens, it is going to read the value of x into Rx. So now when the read happens in process 2, when it reads from x, process 2 is aware of the write that was made into x. And why is that so? So the reason is that release acquire is like causal consistency. So the event x is equal to 1 is causally before y equal to 2. That is why when process 2 makes the read into Rx, it is aware of the fact that x1 was written. In other terms, I can also give the following kind of explanation. Now, release acquire does not allow reordering of 2 write statements. So clearly, I cannot put y equal to 2 first and then x is equal to 1. That is not possible. Neither does it allow reordering of reads. So once again, because of that, I can't just read 0 to begin with. And therefore, process 2 is just unaware of the write of 1. Process 2 is aware of the write of 1 to x when it reads 2 from y. So the summary is that for this example, message passing, we do not see any of these so-called weak behaviors, which means extraneous behaviors, which is not seen in sequential consistency. So once again, if we look at this formal treatment, right, in terms of execution graphs, so the execution graph here, as you see here, now if you look at the read x0 for the second process and the write x1 of the first process, notice that there is actually a path created by the program order and reads from, which is what we call happens before. So there is a happens before relation that connects the write x1 to read x0. Therefore, the second process is aware of the write and therefore it cannot read x is equal to 0. Therefore, in a consistent execution, you will not read x is equal to 0. So this leads us to one of the semantics for array, the declarative semantics.
Sorry, Krishna, can you explain that execution graph again? And what is that happens before edge? How did you get that?
Yeah, sure.
So what are the edges in this execution graph?
Sure. So the execution graph contains the program order. So the blue edges are the program order edges, which are connecting events of the same thread or same process. Then you have the reads from relation, right? So the reads from connects the reads to the corresponding writes. And
So
then you
that
have,
could be, I mean, so what is that? I mean, that's for one execution or?
yeah, this is for one execution. Yes. Yeah.
Oh, this is for one execution.
Yes, 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 yes. So corresponding to every execution, I can draw an execution graph representing that.
So Krishna, could I also ask a question?
Yeah.
Raghavan here.
Yeah.
So I do not understand why there is an edge from the write y comma 2 to read y comma 2 in this execution. So where is the message passing in this?
Sorry, can you repeat it? So why is there an edge from the write of y comma 2 to read y comma 2?
Yes. And also, why is it called message passing? I mean, where is the message passing happening?
Okay, so the message, it's called message passing simply because process 2 is aware of the write of 1 to x, right? So it is like passing that information. So process 2 has received the information that 1 was written to x, which is why it is not able to read 0 into rx. That is why it's called message passing.
And what enforces that ordering from, say, from a write here to a read there?
Okay, what enforces so you want to know why I have the reads from the write y2 to read y2?
Right, why it was not there in the previous model and why it is there in this model. So I do not, yeah.
Okay.
Yeah.
So this is the previous example, right?
Right.
Okay. So in the previous example, as you see, first of all, notice that I did a swap, right? I swapped the write and the read. So the original example was like this, okay? So I had the write followed by the read, right? And I swapped them so I could make the read first and the write later. I'm sorry, because of this keynote. Yeah, okay, I'm back to the slide. So thanks to this, I am writing WY1 first, okay? And in the program order, the swap is now recognized, as a result of which I can read the initial value 0. Raghavan?
So the write also sees a read, sees a write, is it? So what is that MO? What is MO labeled edge?
MO basically is modification order. Okay, so modification order basically means the order in which the variables have been modified during an execution. So to begin with, x and y had both value 0. And then when I write x1, I have modified the value 0 to become 1, right? And then when I write the value y equal to 1, I have modified y0 to become y1. So that is modification order. So here the modification order is connecting from the initial values of 0 to x and y into write x1 and write y1.
So first of all, so you said this is an execution, right?
Yes, it's an execution graph.
No, I mean, does it represent one execution of the program?
Yes, it represents an execution of the program, allowing this particular behavior to happen.
Okay, but this okay. So the program order on this and process 2 is actually the flipped one, is it?
Exactly. That's
Okay.
true. Yes. So what you see here in the execution graph. So notice that this is also what is called a consistent execution graph. I am just 1 or 2 slides away from defining consistency with respect to the execution graph. So consistency basically means, as you asked, this is an allowed behavior. This corresponds to an allowed execution under the release acquire semantics. And as you correctly said, I've got this execution graph because this flipping was allowed. So now the program order has been reversed with respect to these two, these two events in the execution graph, as opposed to how the original program was written.
Okay, so maybe once you define the consistent one, then things might be clear.
Yeah, let's hope so. So Raghavan, is it okay now?
I'm kind of not very clear what is the clapping going on, but I think we'll go on. And I don't understand
Alright.
what clapping business.
One, can I ask? I have a question. Like the program order is how the processor sees the instruction, or how it was in the program.
So the program order basically is, so when you take a process, the events are written in a certain order, right? I have instruction 1, instruction 2, instruction 3 in order. So program order basically connects the events in that order as given in the process.
Okay, but in that first graph, you said when it's swap the program order, shouldn't this program order edge be from on the blue one, the right side process, R to
Yes.
W?
No, so that's what, right? So under the release acquire model, this is an optimization that is supported. And under this optimization, which is supported under release acquire, this is allowed. Basically, you can flip the program order between two events, as long as, they are two consecutive events. One is a read, another is a write of two different variables.
Okay.
So to answer your question, if you are wondering whether there is another possible execution graph where the program order is not changed, the answer is yes.
Okay. What I was thinking is the program order is always predefined before the process starts executing. Is what I thought.
Yes. So when you write a program, there is a certain program order. But when it is executed, if the compiler is supporting certain kind of optimizations, which allows some reordering of events, then the resultant program after this reordering looks a bit different from the original one.
Okay. So this is still from the not reordering done by the processor, but by the compiler. Is it?
Exactly. Exactly. Yeah.
Okay.
So, again, just to kind of...
It could be the processor also, right? Out of order execution. Even a processor may do.
Well, whichever way you want to look at it.
Due to out of order execution.
That is all. See, for me, as far as I am concerned, the way I would like to put it is that this is an optimization that is supported under the release acquire semantics. That's all. So this reordering is allowed under release acquire. It is not allowed under sequential consistency.
No, I mean, the only question is what you mean by the program order edge, right? I mean,
the program order edge is...
It is in this execution after the compiler or CPU has reordered it.
Absolutely.
Right,
May
but
not
then,
be ordered in another execution.
Yes.
Okay, but then you shouldn't be showing this program, no? I mean,
what do you mean?
why don't you just show the program post compilation and then talk about the execution? I mean, the program order edges on.
Okay, so I thought by
So
swapping.
the reordering can happen differently in different executions.
Absolutely. Absolutely. Yeah. So that's what I said. This is one possible execution graph. You can get another execution graph without doing this flipping.
Yeah, maybe things will get clearer if you go ahead.
One question, sorry. So if you have, after flipping it, and if you do this execution, then it's a sequentially consistent execution for the flipped program.
What do you mean?
No. So your original program had, had 2 above 1, right?
Right.
And then,
this was the original one.
You flipped it.
Correct.
And then you did an execution which is consistent with this flipped order.
Yes, that's right. Exactly.
No, it's just to related to Deepak's question. Like, then there will be no difference between sequential consistency and RA.
Yes. So what you're saying is that modulo flipping, you do what you did earlier. And that's the only difference. That's how you want to look at it.
Is that correct?
You can take it that way for the execution graphs.
Okay.
But there is some flexibility in the read from edges, right, Krishna?
Flexibility in the sense, okay, so when you say flexibility, you are saying that if I have a read operation, I can choose to read from a set of writes, right? As long as it does not violate my consistency. So certain writes are out of bounds if it violates my consistency. But it's true that, you know, I may still have a set of writes possible from which I can pick. So what one execution graph depicts is one particular reads from. That's all. So it's possible to have another execution graph where this read is reading from another write.
Right. So, I mean, that's so what Srivatsan was saying. So it's not always a SC, not always a sequentially consistent execution, even after reordering.
Absolutely. But I think what she also wants to say somehow is that if you look at all possible execution graphs that are possible, it is also true that some of them would also correspond to, you know, the standard sequential consistency execution graphs, where I do not do any kind of reordering. So the message somehow is that, okay, if I look at the number of execution graphs possible under sequential consistency and under, let's say, a model like release acquire, the number of behaviors or the number of execution graphs I am going to get under release acquire is more than what I will get under sequential consistency.
Right.
So in other words, I'm going to get extra behaviors here than what I expect to get from sequential consistency. As a result of which, you know,
So
like,
can I ask one? So I feel that it is not just about the reordering allowed in this semantics, but even beyond that, in sequential consistency, every graph must be a total order. And here it need not be, right?
Absolutely.
Even model reordering. So
absolutely,
isn't that difference also there?
That's true. That's true. Yes. Yeah. Okay, so what I wanted to say was in the first store buffer example, what I wanted to show was a non-SC behavior. But it's also true that you will get the standard SC behavior where you cannot read 0 into both Rx and RY. Does that make sense?
Yes, Krishna. Yeah.
Okay. So is the message passing looking fine now? I mean, so Raghavan, is your question about message passing fine, the name message passing?
Not really. I understood the reordering in the other model, but not this one.
Okay. Anyway, this is a standard famous litmus test. It's called message passing. And my interpretation or my understanding for why it is called message passing is because process 2 got the message that Axis1 was written by the first process. I mean, this, of course, just my interpretation because it's a well-known litmus test. Did the, you know, whatever, the people who gave the name, I don't know if this is what they had in mind. This is my interpretation.
Yeah, the message is basically that Y is non-zero, right? I mean, that's the message that is going from.
And because of the causality, you know, 1 was written into X before Y got the value 2.
Yeah, I mean, that is coincidental, but the message that is going across is that Y is no more 0.
Sure.
Well, is it a total order? No, not really. So all reads and writes of the same variable are totally ordered. Is that the?
Yes, that's right. Yeah. So see, if you look at just a modification order is a total order per variable.
In this model, but not in the other model.
Yes.
Not in the release acquire. Okay.
Yeah.
No, I think this is the same model only, right? This is the same release acquire.
Say in this example and that example. Maybe that's what Raghavan wants to say.
Yeah.
No,
So
these are two different models. I thought these are two different models, weak memory models.
No. I am talking only about one weak memory model in this entire talk, and that is release acquire.
Oh, okay. I thought message passing was a stronger memory model than.
No, nothing. Message passing is the name of the litmus test. Store buffer was the name of the earlier litmus test. And they are both, so all the main message that I wanted to convey when I said this does not exhibit weak behaviors, whereas store buffer exhibits weak behavior. So the main reason is that because of this message passing from process 1 to process 2, I do not get these extra behaviors which are not, you know, beyond sequential consistency. So here, for example, I do not read 0 into Rx, right? Even though it is under release acquire. Whereas the first example allows some extra behaviors which I do not see under sequential consistency.
Okay,
That's-
because the swapping happened there and did not happen here.
Absolutely.
Okay.
Okay, so let's see. Okay, so we were talking about the declarative semantics for release acquire. So the declarative semantics for release acquire is, well, release acquire because that's a model and, for today's talk. In general, declarative semantics is given in terms of execution graphs. So we say that an execution is consistent, provided you can, come up with two relations. One is the reads from relation, which maps reads to corresponding writes, so that the happens before relation, which is the transitive closure of PO and RF, happens to be irreflexive. Okay, this is one. And you should also be able to find a modification order, which is a total order on same location writes, same variable writes, so that you have the following three conditions. Okay, so your modification order should not contradict with the happens before. This one. The second one says that you cannot read overwritten writes. So if you think of message passing now, we were not able to read x is equal to 0 because it was overwritten by x is equal to 1. So this is why you did not get that, that strange behavior under message passing. And the last one again is similar, but I'm talking about atomic read writes now. Pertaining to atomic read writes, again, the condition is that when I read, I should read from the latest written according to the modification order. So that's it for the declarative semantics for release acquire. Okay. So any questions?
Yeah, sorry. So, you, okay, so just to understand this, so you define the read, you have an execution and you want to know whether this is allowed under RA.
Yes. So in some sense, when you draw the execution graph, the way you place the reads from, right, which is like one of the edges in your execution graph, the choice of your reads from must be in such a manner that your program order, the transitive closure of PO and RF should be reflexive. That is one condition. And the second one is that your modification order does not go in the opposite direction of, basically MO should agree with HB.
Okay, what does that mean? That if I, okay.
So for example,
if I have a modifies after, then that should also happen after.
Exactly. So the way it will affect your, so if you look at the second one, right? If I try to read from a variable X.
So where have you said in the slide, where did you say that MO should agree with HB?
The first figure.
First figure.
Yeah. So notice that my MO is going in one direction, HB in another direction.
Oh, okay. I thought you're defining it in the slide. You're only showing pictures.
No. So I'm saying these should not happen.
Okay.
So your MO should be such that you do not see these three things. So the MO you synthesize, must respect so that you do not see either 1 or 2 or 3.
Okay. Can you explain 1, 2, and 3?
So the first one basically says what? Okay. So I have written the value V after the value U, right? Because the modification order goes from writing U to X to writing V to X. Right? So which means V is a later write than U. Now, if I have happens before in my graph, now this happens before is not just one edge, right? It is a sequence of edges. It's a transitive closure of PO and RF. Now, if it so happens that your PO RF transitive closure connects the other way around, then this MO is not a consistent MO. It's not a good way to define MO. That's what the first one is. Okay, what does the second one say? The second one says that, okay, you are trying to read from the write XV. Okay, you have the read XV, you have read X, forget about the V, you have read X. If you want to read from write XV, but if you already, have a path from the write of XU to the read X, and if this write of XU is a later write than the write of V into X, then you cannot, define the reads from that stale write or a overwritten write. That is what the second picture says. And the third one is same, basically, right? Atomic read write is basically performing a read and a write atomically. So it's not really very different.
Yeah, I got it. Yeah.
Somebody was raising a hand.
Yeah, hello, this is Abhishek. Krishna, I wanted to just ask you, what's the difference between the second one and the third one? I mean, I mean, yeah. So the third one I couldn't get it. What
So
do you
the
want to say?
third one is basically what is called an atomic read write. So an atomic read write is, you perform a read and then you do the write so that, no other instruction comes in between. So in spirit, there is no difference, right? The emphasis is that, okay, after you did the read and when you do the write, right? So when you do this together, you are reading, right? In atomic read write, you're first trying to read something into X. So when you do that read, respect your whatever, the same kind of thing. Do not read from stale writes or old writes, overwritten writes. Maybe it will become clearer when we look at the operational semantics, perhaps.
So even if you, let's say, give up this third one, doesn't it, is it implied from the second one? Because second one already has this.
It should, yes.
Okay.
So one of the reasons I put this is so that I am going to use atomic read write later in my talk, and it's an integral part of release-acquire. So, this could be the first slide where I introduce atomic read write, if you like it that way.
I see. Okay.
So if you want to know the meaning of the notation, right? ARW X V V prime, what that means is that, okay, you try to read the value of X so that it is V. So you try to read V, and then you override that V with the value V prime.
So this is RMW kind of command, right? This is RMW kind.
You can call it RMW, you can call it read, modify, write, you can call it compare and swap, you can call whatever you want. It's the same thing. Yeah. It's just that, okay, I'm calling it atomic read write because it's also one of the things.
Okay, so one more thing, if you allow, I want to ask. So the flexibility that you get in HB, in defining HB, is from basically RF, right? Not PO. PO is well defined when your program is given.
Sure.
So the conflict can arise from the selection of RF and MO, right? MO and RF is what is in our hand.
True. So what you're saying is that the readable set, right? The so-called readable set is basically has to be chosen carefully.
Right. Yeah. Okay. Yeah. Thank you.
So Krishna, sorry, one more question about the. So there is this happens before consistent model, right? Which is basically you have this happen before ordering, like you've similar to what you've defined, and you say that your write scene essentially, write scene is similar to your read from.
Right.
Should be consistent with the happen before order in the sense that you should not see something that happens after you.
Absolutely.
Right, and you should not see something which is stale.
So Deepak, in that one there is a separate happens before relation, but here it is an HB is just a
defined in terms of PO and RF.
There is no independent.
Right. Okay. So you're saying, okay, this RF is right.
I think Deepak was trying to talk about future rights.
Right. So there, the HP is defined in terms of a lock, release, acquire.
Yes.
Whereas here it is, you first define the RF and then you get the HP. Okay.
That's right. Yeah, exactly. So synthesizing RF also somehow synthesizes.
Okay. So then the read from will always be consistent with HB.
Yes.
Okay. Then what is the issue? Then the only thing
the modification order, right? So the MO and your HB cannot contradict each other. That's all.
Okay. Okay, fine.
Okay, so I guess I'll move ahead.
So can I ask? Sorry.
Go ahead.
Sorry. So this PO, is it the fixed order that you had initially, or is it after reordering?
So PO is, let's say, in case you don't do any reordering, the original one.
Okay.
Or when you do reordering, what you get after reordering. So when I say PO here, it is the PO as in the execution graph, which could be either after reordering or before reordering, depending on what you choose.
Okay. And this I understand now. So the second question, MO, isn't it derived from HB and RF, or like, how do you get the MO?
So MO basically is, you see, so when you, okay, so suppose you had done some reorderings, right? Now MO basically comes because, okay, let's say one process makes a write on X at some point, and another process makes a write on the same variable later down the line, right? So the possibility is that you can define MO either from this write to this write or from this write to this write if they are from different processes. That's a possibility, right? So
I mean, maybe I could reinterpret the question as why do we need the MO at all? Why RF alone is not enough?
you mean to say you can define MO in terms of RF?
No, why does the MO, why is MO required at all? Because
Okay.
all I eventually care for is what do I read for a read. So who cares about this MO?
Well, so here for the consistency condition, it is defined with MO.
Yeah, but you could as well define. Okay. Oh, sorry. Okay, maybe that the issue is that this RF is used to define the HP. So then
Yes.
I don't think there's.
Yes, at least
Yeah.
I don't know without MO how you can define the consistency notion here.
Does MO depend? Does it relate to the reordering that you did? Does it have something to do with the? Sorry, I'm stuck here.
MO, no. See, the reordering would not affect MO.
Okay.
The reason being, see, so the MO is interesting only when the writes happen in different processes, right?
Okay.
Somehow the point is in the same process, right? If you are doing two writes to the same variable in the same process, then okay, if you reorder, you know, right, whether you are going to have a different MO. So notice that release acquire does not allow you to reorder two writes.
I see. Okay.
Right. So if I have this write and a read, then I'm doing this one. So the interesting, so somehow, you know, if you are, it's possible to have MO from the same process. Certainly I can have a write later and a write before, but that is not going to be affected. The interesting MO comes when, you know, there is a write happening in process A and another write happening in process B.
Okay.
Where it's possible that I could have drawn the edge this way or that way.
Okay.
And it's possible that drawing the edge only one way is going to be consistent for a certain execution graph. And drawing the other way may contradict what happens before.
I see. Okay, fine. I understand. Okay, this has nothing to do with the RF. This is between two, yeah, okay, thanks. Yes. Yeah.
Well.
I still didn't understand why the MO is needed. Why is the MO needed? Because it seems that RF is enough. Like what? I only care about what I'm reading. Why does the order of writes matter? Beyond what I read from intuitively.
Okay, I would agree that maybe you do not worry about the MO for checking assertions. Maybe that is fine. But then maybe what you want to say is you want to redefine consistency without the MO. That's what you want to say.
Yeah, maybe. So I think we will go ahead. Maybe I'm not very coherent on this. Yeah. I'll drop this question.
Okay. So
okay. Yeah, Krishna, can I ask one thing? So I get, super confused when you say this swapping of two statements from the same thread. So this PO, I was assuming that is actually defined based on the program, how the static syntax of the program, not after reordering kind of thing, right? Because then you have a program and you now want to know what is consistent according to RA semantics. So
yes.
If you reorder, two statements in the same thread, I think you can do a lot of many things. Which is not possible in RA. So are you sure? This PO is before reordering or just by looking at the program?
No.
I was assuming. Okay. Yeah.
No. So you can have the original PO, as you said. But after reordering, what I get is a different PO, right? But that's a PO because this is a reordered program which is allowed under RA. It is fine. So notice that I am not allowing all kinds of reordering, right? So for example, if I have two consecutive writes, I will not change the PO between them. The PO will change only when I have a write of X and a read of Y, and X and Y are different variables and they are consecutive.
Could I put it that the original order doesn't matter and they are only looking at the PO after the reordering, since it's an execution? Are we even trying to relate this PO with the original PO? In this whole, or we don't care about it.
See, the point is this, right? If you are given a program, if you decide to interpret under release acquire, Okay, so one, you can choose to do no reordering at all, right? That is still allowed.
Right.
Now that is one kind of, so take the original program, take it as it is, try to draw consistent execution graphs coming out of that, which basically would be just the SE semantics, no change. Now consider all possible reorderings of the given program by respecting this condition for reordering, right? Only reorder this write read when they are in different variables. Now this can happen in multiple places. So you can choose to reorder maybe at one place, two places, do all possible combinations. Now this is resulting in programs which look very different from the original program. Corresponding to each of this, you can now have consistent execution graphs where when you say PO, I mean PO with respect to your reordered, the different looking program.
So Krishna, is PO a partial order, not a total order?
So
I mean, on the instructions in one thread.
It is a total order, right? Because I mean, take any two instructions I and J, either I comes before J or later than J.
No, I mean, in the sense that if I have a like you had that example, a read of a write to X and a read from Y or something like that, right? Which you, so those, I can say those are not ordered by PO.
I see. Okay. What you're saying is because I can do a reordering of those, somehow you can consider them as not to be having one absolute order when they begin.
Yeah, then this makes sense. I mean, then you're looking at a program and PO is well defined. I mean, it doesn't matter how you, I mean, it
yes, so
it allows
if you
reordering.
Say that because they are susceptible to reordering, if you want to say I would consider them unordered, that's a possibility. Or the other option is, well, you know, as I said, do all possible reorderings and all of them are, it's like a different program, but derived from the original program because it's allowed under the semantics, and then look at your execution graphs under those. Okay, so do we have more questions?
Krishna, I don't have more questions, but I have a comment. Given the time that we are in, this has become a talk on tutorial on RA. I'm wondering if it's a good idea to have one more session where you kind of do the continuation of, as in, I don't know.
We will see how it goes, right? So let's see, what's the time? It's 7:45. So let's see how much I can finish by 8 today. And I will tell you what more I have in store. And if everyone feels it's good to have another one, we can have another one.
Oh.
Whatever.
Yeah.
I mean, I'm flexible at this point of time.
Yeah, sure. No, I mean,
okay,
this has become like a question answer session on RE. So yeah, thanks.
That's fine. Okay, so I guess I will move ahead right now. So the thing is, this is just a few good things about release acquire, which is like well known. So the good things are basically, so let me start with the supports optimization part. So we know that sequential consistency does not allow reordering of writes to reads. And thanks to this, it is, you know, not performing well under the modern hardware architectures. Whereas release acquire supports, you know, this optimization of write to read and therefore enjoys better performance. So that is one of the good things about release acquire. Well, good or bad, depending on if you are looking at performance versus, you know, verification of a program under release acquire. Okay, it has a very intuitive semantics. So the declarative semantics is what I've spoken till now, but there is an equivalent operational semantics, which I will start talking from the next slide onwards. And it has been proved that the declarative semantics and the operational semantics are equal. Okay, I think somebody has shown this using the Koch theorem prover, that what you can do under the declarative semantics would coincide with an execution you obtain, which is consistent with respect to the operational semantics. Then if you want to reason about programs under release acquire, there are some program logics which people have developed. So that's again a good point in favor of release acquire. Now, when we started, right, we said, okay, so we have all these various kind of architectures like power, TSO, etc. And the weak memory exhibiting at the level of programming languages for release acquire. So now if you want to, you know, kind of understand this chemistry between weak memory at the programming language level and weak memory at the architecture level. So there has been some work where you can basically, you know, compile a program under release acquire so that it runs on a TSO machine or a power machine. So that is some work which is already there. And the last thing is that, okay, you take a program under sequential consistency. If you know that there are no data races with respect to sequential consistency, then what you know also is that you don't have to know anything about release acquire. What the guarantee is that if under sequential consistency, you have no data races in your starting program, then you will not get any weak behaviors, or you will not get any extra behaviors, as we saw on the store buffer example. Okay, so these are all some of the good things. And of course, if you look at this particular thing, right, absence of data races implies no weak behaviors is true for release acquire, but it's not true if I look at the full C11 model. So basically, all that this slide is trying to say is that release acquire seems to be a reasonably well-behaved subclass or fragment of C11.
So, but when you say extra behaviors, you mean non-release acquire behaviors?
No. When I say extra, my reference point is always sequential consistency, right? Because it's a traditional behavior. So whenever I say extra is more than sequential consistency allows.
Okay. That's a bit, I mean, isn't it kind of vacuous that if the program is guaranteed to be sequentially consistent, there will be no extra behavior. So isn't that like a vacuous statement, or did I miss something?
No, I didn't say it is sequentially. I'm just saying if you have no data races under SC, then you have no weak behaviors. Which means if you have data races under SC in a given program, if you interpret under SC, then I am not commenting whether or not it has weak behaviors. It may have extra behaviors.
Okay. The other question is, where is the release and acquire in this model? Why those two words?
Great question. Okay, so yes.
So finally, we have a great question after dozens of silly questions.
I didn't imply that. I really didn't imply that.
Okay, no, I'm just joking.
Yeah, I got it. No, the reason I said great was, I usually, whenever I talk about release acquire, I normally used to say, what is the release, what is the acquire? I will say that now, but my feeling is, you will appreciate the terms release and acquire when you look at the operational semantics. Okay, so now we have two kinds of writes under the C11 model. Okay, one are what are called relaxed writes. Another is called release write. Now for reads, there is this relaxed read and acquire read. Okay, so the term acquire is always tagged with a read, and the term release is always tagged with a write. And what the meaning is basically is the following. Okay, so a write is a release write. If you take a program, if a write, so these are basically memory access modes, right? The release is an access mode, relax is an access mode. Just like your acquire is a way in which you access the memory while reading, and relax is yet another access mode when you try to make a read. Okay, so if you have a release write, the thing is that a write is a release write, provided you can, let's say, swap it with anything that comes later, but nothing that comes before. And an acquire read is one where you can swap it with anything that comes later, but not comes before. Okay, so this is typically what it means to say release and acquire. But for me personally, intuitively, the terms make more sense when you look at the operational semantics, because that tells me what I am releasing and what I'm acquiring. Okay, so because when I make a write, I am releasing some information, which is why I think of it as a release write. And likewise, when you make an acquire read, the reason I call something an acquire read is because I'm acquiring some information, which is why this read is called an acquire read for me. Okay, so maybe after the operational semantics, I hope these terms release write and acquire read would make more sense.
Okay.
Abhishek had a question, I think.
Yes, I had a question. So you always say this is a fragment of RA, right? I mean, you're talking about, so what are you leaving? I mean, when you're talking about this fragment?
See, in full C11, just as I said, my writes could be relaxed writes or release writes. My reads could be acquire reads or relaxed reads. So when I talk about the release acquire fragment, I'm assuming that all my writes are release writes, all my reads are acquire reads.
Okay, I see. Okay.
So it's basically assuming, that take C11, interpret all writes as release writes, interpret all reads as acquire reads, and that makes you RA.
Okay. So in your program, I mean, you're assuming that all writes are release rights and all reads are okay. I see.
Exactly.
Without
because typically, if you just say C11, you can have a mix of these, right? Some writes could be relaxed writes, some of them could be release writes, and likewise, some reads could be relaxed, some reads could be acquire. It could be a mix.
Okay.
Which makes things even more complicated. So somehow because I'm restricting the kind of writes and restricting the kind of reads, it is just called release acquire.
I see. Okay.
Okay, so should we start looking at the operational semantics? Does it make sense?
Yes, I think we should.
All right, thanks. Okay, so this is again proposed by, it appeared in 2-3 papers. So I'm just referring to those when I talk about the operational semantics for release acquire. Okay, so, in this illustration, I'm having 2 processes. In general, you can have some n number of processes, doesn't matter. So the memory is, as you see here, this ellipse thing is my memory. So the memory is basically a pool of messages. Now let's look at a message. Now, if you look at any message here, it has this green compartment and the blue compartments, right? So the green is basically talking about one fixed variable, and a message is added to the memory pool every time I make a write operation. Okay, so it's a memory pool of views or messages, as you may want to call it. And every message here is inserted into the memory pool when the write operation happens in some process. Now, these numbers below are basically logical clocks per variable. So it's vector clock, logical clock, whatever you may want to call it per variable. So I'm assuming I have 2 variables, X and Y. So a message. So the idea of this slide is just to tell you how a memory pool looks like and how does a message in the memory pool look like. Okay, so it basically has these 3 components: a variable with a value that has been written to it. That's one part of my message. The other components of my message are this logical clocks per variable. Okay, so if you look at any of the messages here, so it's either a write to X or a write to Y. So when I look at this memory pool, all that I know is that I have seen 2 writes to X somehow, and I have seen 2 writes to Y. It doesn't tell me which process is written. It is immaterial for me. It just tells me the value written as well as the logical clocks of all the variables at the time when the write happened. Okay, that is all I know. Now, when a program begins execution at the start,
so the logical clock are that process that did the write, I guess. Is it right? So I guess every process will have a different view of the logical clocks.
Yes, I'm coming to that.
Okay.
Yeah. So, when a program begins execution, a typical message, right, will be basically the value of, okay, I'm assuming that when I begin, all variables are value 0. Okay, that's how I begin. So when I look at my memory, the message pool or memory pool, whatever you may want to call it, a message for X will look like X is equal to 0 with all the logical clocks having value 0. I'll have a unique message for Y again with value 0, all the clocks having value 0. Okay, so to begin, the size of the memory pool is equal to the size of the number of variables I have in my program. That's it. So to begin, it's a finite sized object. And we will see that as the program continues to execute, it will keep growing. Okay, so logical clock for X, logical clock for Y. Yes, Abhishek?
Yeah, so you have a clock corresponding to every variable or what? I mean, I can see 2 blocks below every this right? So do we have clocks for each variable or?
Yes.
Okay.
Yeah. Okay, so now let's look at how a configuration looks like. So I have just one process depicted for this particular slide. So this process has 3 instructions. It has a read from X, a write to X, and a read from Y. So the thing you see in blue is the local view of that particular process, which as Raghavan pointed out, the local view of process 1 could be different from the local view of process 2. Again, when I begin, the local view of all the processes are 0 for all the variables. Okay, so when this started, it would have been 0, 0, but I'm assuming it, after some time. Okay, so now let's see how I make a read operation. So the first one is a read operation, right? So how am I supposed to read from the memory pool? So now notice that the memory pool has multiple messages for X, and I'm trying to read from X. So the first thing I'm going to do is I am going to select a view which is relevant to me in the memory, which means I'm going to ignore all the Y messages because they do not pertain to me, right? I'm supposed to read from X after all. So now I have 2 messages corresponding to X. Which one should I read is the next question. Of course, the values are 1 and 3. So if I read from one message, A will get the value 1. If I read from another one, A will get the value 3. So here is where I'm going to use my local view, which says that the timestamp for X is 3. In other words, process 1's knowledge about X's progress, okay, in this entire execution is 3. 3 some number, it's a timestamp. And the logical clock corresponding to y is 2 for process 1. So I now look at my memory pool. There are 2 messages. I can choose from these 2 messages that message where the logical clock for x is 3 or larger than 3. So when I zoom into like this, I realize that one of the messages is obsolete for me. I cannot read it. So I ignore that. So the only message I can read from is the one where the value for x is 1. Okay, so that is the value I'm going to read. Now, what happens when I read? Okay, so when the process 1 reads from this particular message, it has to update its information to say that, well, it's going to merge its local view with the timestamps or the logical clocks in the message that was there in the memory pool. So the merge operation is just a component-wise max, which means that at the end of the read operation, the local view gets updated to 4 and 2. And of course, the value 1 is what A gets. Okay, so this is how a read operation happens. So, any questions?
So the value for the Y's clock also increases by 1, is it?
No.
So it was
2. It continues to be 2 because when I look at the message in the memory pool, the timestamp for Y was lower than what the processor's local view for Y was already.
okay, sure.
So now maybe this is possibly the first time when the term acquire could make sense.
So we have to take the max on even the Y's clock,
Yes. Yes.
even though we are not reading the value of Y.
That's right. That's right.
That's
So
a bit
as you see,
surprising. That's a bit surprising.
Oh, well, maybe that is why the term acquire is given. No, I'm acquiring information from the message I'm reading. So somehow all that this says is that, okay, so imagine that this message, okay, the timestamps were not 4 and 1, but 4 and 5, let's say. Okay. So now if the timestamps were 4 and 5, or hold on, let me talk about right now, then we'll come back to this, then it'll make more sense. Is that okay? The next slide is right.
Okay.
Okay, my point was to talk about the terms release and acquire. And I think it will make more sense when we see how a write operation happens. And then we will see, okay, whether the terms release and acquire have some meaning with how these timestamps get updated. Okay, so this is as it stays. Yes, so you're right. At the moment, when I take the max, it's a per component max. So in some sense, the variable I'm reading from, of course, acquires the view directly because here it is larger. And as I said, if I had 4 and 3 instead of 4 and 1, the timestamp for Y in the local view would also have increased to 3 from 2. But here 2 is larger than 1, so I'm not changing the local view of the process. That's what it is currently. Okay. Now let's see what happens when a read happens. Abhishek, hold on. Let me finish right, and then we can talk about it. Okay. Okay, so this is what we said already. Now let's look at a write operation. Okay. So now the next operation is the write operation. So I'm supposed to write x is equal to 2. So what do I do? So the first thing is that whenever I make a write, remember, I'm supposed to add a message to the memory pool. Now, when I add a message, what are the components I should add, right? First, I'm going to write the value 2. So the green component will say x is equal to 2. That is fixed in my message. I'm going to add to the memory pool. Now, when I add x is equal to 2, I have to now choose a higher timestamp for x than my current local view. So my current local view for x is 4. So I'm adding a new message. So it must be something that is larger than my local knowledge of being 4, which can be 5, which can be 6. But it should not be a value which is already there in the message pool corresponding to x. So for example, I cannot choose the timestamp 9 for x. Okay, when I make the write, because you see I have a message for y where the timestamp of x was 9 already. So I choose a fresh timestamp for x, which is larger than my current local view for x. So that is what I do. And I am going to add it to the memory. Okay, so create a new local view, and it should be newer than yours, and it should not be in the memory. So I can choose 5 or 6, whatever I want. I've chosen 5. And I'm going to add it to the memory. Okay, copy new view to the memory. Okay, so this is what happens. Okay, so now that we have seen write and now that we have seen read. So now if you think of the term release write and acquire read. So when I say acquire read, I'm basically, whenever I'm making a read, I am going to take a message from the memory pool. I am acquiring information about the local timestamp of every variable which was present in that message, even though that message was, obtained when I wrote to a certain variable, right? So I'm acquiring information from all of these guys when I make this write, when I make this read. So it's an acquire read in that sense. And a release write is releasing to the memory pool or releasing to the world the process's local view it is getting released to the world, right? So now whenever a new process makes a read by taking a message that is released by a certain process, it basically gets information about, what was the status of this particular process at the time it entered this message to the memory pool. So it is like releasing its local view, and the reader is acquiring information from the message whenever it reads from. So does that make sense? The terms release and acquire?
When you do a normal write is a relaxed write, right? So then also some information is being given into
Well. So when I do first of all, I'm not going to talk about relaxed write in this talk. Okay. When I do a relaxed write, I'll tell you independently that this merging happens. But at that point of time, I do not care about the merging of timestamp of other variables other than the current variable I'm reading. So in particular, if your x equal to happen to be a relaxed write, okay. So relaxed write, no, what I think your question is with respect to reads, right? When you read, you don't want to acquire information for others. That is what your question, right, Alvin?
Yeah, either way, like what would be the difference between the normal read or write and the other
Yes. So let's talk about reads first, okay? If the read was a relaxed read, okay? So if a equal to x was a relaxed read, now notice that when I read it, I merged and updated, both the timestamps, right? One for x, one for y. Both of them I updated. But now if it was a relaxed read, I would update the timestamp of x, but not of y. So Raghavan said he found it surprising that both of them got updated, right? So if it was a relaxed read, maybe it would meet Raghavan's expectations that I would not update the timestamp of y. I would have updated only the timestamp of x. Somehow I'm not worried about y. That would have been a relaxed read.
Okay.
And likewise, if I do a relaxed write, when I release information into the memory pool, I would of course update my current timestamp to a higher one for the variable x. But the others, I would just say bot. I don't care.
Okay, but the release write would essentially put messages for all the variables with the.
You mean timestamps for all variables?
Okay.
Right?
That's but not the values of the current all the variables. Only the timestamps you.
Yes. So Alvin, so whenever a write happens, okay, be it release write or relaxed write, I am still going to add messages to the memory pool. Okay, that part is constant. Adding a new message to the memory pool happens whenever I make a write operation.
Okay.
The only difference is if it is a release write, I am going to release my complete local view, okay, into the message pool, right? Because as you see here, when I made the write, I updated my timestamp for x. Whatever my timestamp for y was, I released the entire thing to the memory, right? So I'm releasing the whole information. If I was a relaxed write, if I'm writing to x, I would update to the memory pool only this 5, okay? Because that is anyway increased. It was 4, it became 5. But I would suppress the information corresponding to y. I would not talk about it.
Okay, so you would essentially have, is it like 2 messages or?
One message. I am always writing only one message, right? The only difference I'm saying is when the message is written corresponding to a release write, you have all timestamps which agree with the timestamps of the local view from the process. If the message is inserted as a result of a relaxed write, then the only timestamp you will see is pertaining to the particular variable you have written to. You would not, for example, so if you want to, think of in terms of x and y, right? If x is equal to 2 was a relaxed write, the message you add to the memory pool will say x is 2, 5 bot or, whatever, nothing, if you like.
That was what would be put in the other slot.
Yes. So now, in particular, right now, if again, right, if it was a relaxed.
Krishna, I had one more question. In the operational semantics, is there an assumption that at any time only one process is executing an instruction? because I have to look at the pool of all messages to see, what is the largest number, etc. So,
Yes.
and that pool can't change on me while I'm looking at the pool.
That's right. That's right. So I'm assuming that, when a process is making a write, only that guy is writing. Yes.
The same with reading also, because I have
Correct.
to find a, yeah.
Absolutely. Yes, 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 yes. So you see, somehow, right, where this operational semantics is heading to is you can imagine it as a transition system, no? Basically, right? So I have a current configuration. What does the current configuration say? The current configuration says for process 1, where is my program counter? What is the local view? What are the values of my registers? And what are the values of the variables according to what the program has seen? Okay, this is like a typical configuration, right? So when I make a transition, I'm assuming that, okay, pick a process. Now let this guy do something. Let this guy read or write, and as a result of which you get an updated configuration. The memory pool may change if it was a write. The memory pool will not change if it was not a write, and so on and so forth. Okay, let me do one thing now. If this operational semantics is now, of course, I have not spoken about atomic read, right? That is the next slide, but I don't need it right now, okay? Let's go back to the store buffer example, no? The one which had extra behaviors, extra as in outside sequential consistency. Now, let us see if you use the operational semantics, okay? So forget about the swapping. We don't need the swapping at all. I don't need the swapping. I'm just going to see the program as it was. Now, by looking at the program, can you now see why I can read 0 into RY and 0 into RX by following just the operational semantics? So how does the memory pool look when you start? When you start, you have a message with X is equal to 0, timestamp 0, 0. And you have another message with value Y equal to 0, timestamp 0, 0. Right? This is how the memory pool looked like with 2 messages when I begin. Okay. Now, I'm going to execute X is equal to 1, let's say, okay, without loss of generality, let me start executing the first process, the first write of X is equal to 1. What am I supposed to do? I'm supposed to choose a higher timestamp than 0 because the current local view for the first process is 0, 0, right? So let me choose timestamp 5, okay? That's a timestamp I'm choosing for X. So my local view, process 1's local view will become from 0, 0 to 5, 0. I see a new message in the memory pool, which says X is 1. The vector is 5, 0. Agreed? So far, so good?
Okay.
Yes.
Yes. In the memory pool, right? I have 3 messages in the memory pool, the 2 initial ones and the new one with timestamp 5, 0. Now let me try to read the value Y, okay? RY equal to Y. I'm trying to make a read operation, okay? So I look at my memory pool. Forget it. Let me not read right now. Let me also execute the first write of process 2, okay? Because that would make it slightly more interesting. Okay, now process 2 is going to write 1 into Y. What is its local view? 0, 0, right? Because it has done nothing so far. So when it makes a write, it is going to add to the message, the memory pool, a message with Y is 1. The timestamp of X of process 2 is 0, does not change. For Y, it can choose any value larger than 0. Let me say chooses 7. Okay, so it is adding to the memory pool the message where Y is 1. The timestamps are 0 and 7 respectively. Okay, so at the end of this, both processes performed a write. And my memory pool has 4 messages, the initial ones with 0, 0 with the timestamps. The first process has added a 5, 0 timestamp with X is 1. The second process has added Y is 1, timestamp 0 and 7 respectively. Okay, now we are going to read. Okay, let's say process 1 is trying to read the value of Y from the memory pool. What is the local view of process 1? 5 and 0. Okay, so timestamp of Y is 0 in the first process. Now, what is the rule for reading? I look at my memory pool. My timestamp of Y is 0. I can choose from the memory pool any message where the timestamp of Y happens to be 0 or larger than 0, correct? Now, what does that allow in particular? In particular, it is going to allow me to read from the initial message corresponding to Y, which had timestamps 0 and 0. So because this guy's local view is 0, it can read from the initial message in the memory pool. And when it does the merge of the two views, its local view being 5, 0, the view in the message corresponding to Y being 0, 0, the local view does not change, but it reads the value 0 into Y, 0 from Y rather. Likewise, when the second process now makes a read, okay, read from X, what is the current local view for process 2? The timestamp of X is 0, timestamp of Y is 7. So its local view is 0, 7. Again, it is trying to read from X. So it can choose from the memory pool any message whose timestamp corresponding to X is 0 or larger. So of course, it is free to read, the message added by process 1, but it need not, right? It can easily and happily read the initial message corresponding to X where the timestamp of X was 0, which means under the operational semantics with the release writes and the acquire reads, it is eminently possible to get 0 and 0 respectively. And I don't have to talk about any reordering, nothing. I can take the program as given. I just need to follow this, timestamping, adding messages, respecting a few rules when I write messages and reading them.
So we also have to show that MO or the, what was that, MO, the right order is, those 3 conditions have to be satisfied, and those are also satisfied in this case.
So that's a good question, right? So now let's think about it. So, okay, so whenever you make, okay, let's take 2 cases, okay? First case, think of 2 writes performed by the same process, all right? So now in my process 1, suppose I had X is 1 and the later X is equal to some 3, okay, coming later. So now, obviously, when the same process is adding 2 messages to the memory pool, the timestamps it will choose for X will be, the later one will get a larger value than the earlier. That is obvious, right? Because it's a rule that I have to choose a fresh one. It must be larger than my local timestamp. Therefore, a later read will get a higher timestamp. Now, suppose that you had, let's say process 1 is writing 1 to X. Let's say process 2 is also writing another value to X. And then let's say process 1 is again writing to X. Okay, so I have 2 writes in process 1 to the same variable. I have a write in process 2 to the same variable. Okay. So now let's say the first write by process 1, the timestamp chosen was, let's say 3. Now when process 2 makes a write, remember, it need not choose a timestamp larger than 3 because its local view for X was 0, right? So it could have chosen 2. 2 is larger than 0. It's fine. But that's a possibility. But it could have also chosen maybe 4 or 5. That's also possible. So if you are thinking in terms of increasing timestamps to model modification order, that is not always true. As I said here, because here, if you think in terms of modification order, the first process wrote X. Then in this particular execution, the second process writes X and the first process writes X again. But the timestamps chosen by them could be 3 by process 1, 2 by process 2, and then 4 or 5, whatever by process 1 again. This is possible. What is also possible is that, okay, the timestamps could have been 3, 4, and 5. That's also possible. So does that make sense?
Yes, Krishna, this was very useful. So, as in, that's why I think probably the same. So now we kind of see why there is no extra behavior in the second example.
You
this
do?
X equal to Y equal to 2.
I see. Okay, I'm happy to hear that.
No. I mean, maybe I got it wrong, but so because when you.
No, you're right. Come on, yeah. At the end of all this, don't say that you got it wrong.
No. So so because when you write Y equal to 2,
yeah,
the message will also already have something bigger than 1 for X.
Great job.
So, no. Okay.
No, you're right. You're right. So basically what you're saying is that when the second process read the value for Y, which is different from 0, it acquires the timestamp that was chosen by process 1 corresponding to the write of X equal to 1.
Yeah.
Which is larger than the initial timestamp 0, which is why it cannot read the initial message.
Yeah. Okay. So that's why the message has been passed now.
If you like to say so.
Yeah. Okay. No. I mean, yeah. Okay. Yeah. Thanks. Yeah.
Okay. So now tell me what should I do? Because you see, I have just finished the operational semantics for read and write. I still have for atomic read write. And then after that, what I have is a sample execution. And only after that am I going to talk about the problem of interest, which is the reachability problem for programs under release acquire. So you can tell me what should be done.
Yes, I think it'll be good to have another talk, because I believe even if we take another 15-20 minutes,
no, nothing will happen in 15 minutes.
Correct. That's what I'm saying. And
All right. So yeah,
But Krishna, are you fine with
it depends on when.
the 3rd of January, the next slot?
Okay, by then people would have forgotten everything.
That is also true. Yeah. Any ideas, Srivatsan? Do you have any suggestions?
I think if we can just go through the recording, just
Yeah.
to
So
get,
the slides will be available, and we'll make it explicit that this is part 2 of the
It's
talk.
like a punishment, you know. Sri, you are making it like a punishment. We have to look at your recording and then come for it.
no. I mean, so, but Krishna, you're fine with giving a talk again.
Yes, as of now, I'm fine. If something doesn't work out, I'll let you know. Hopefully it works.
It doesn't have to be Jan, it can be any slot. We can,
Got it.
1
Yes,
month,
yes.
2 months should be the same. Yeah.
I understand. Sure. Yep.
But this was really very useful because there were lots of questions and
Yes, I agree. Yes. Totally. I think useful for me too, you know, because, you know, when you try to reason about some of these things, you become clear.
So sorry, maybe just one question. I understand the operational semantics. Probably I also understand the declarative semantics, but I don't see the link between the two. So like why that execution graph, is it easy to?
Yeah, so you're asking for the proof of the equivalence between what do you say? See, what you want to ask is take a consistent execution graph, which is given according to the declarative semantics. Can you now, you know, get a consistent execution respecting the operational semantics? In other words, what you want to say is that, okay, here is an execution graph where I know this is what was read from, this is the modification order, etc., etc. You want to say that, okay, this can also lead to the following run in my transition system, where the configurations were, you know, blah, blah, blah. And, you know, when I read, I'm basically doing the same read as told by my execution graph. That's what you want to ask.
Correct. Yeah.
I don't think I'll get into that.
Okay.
But I guess
yeah.
Go ahead. Sorry, I didn't hear you.
No, go ahead. Yeah.
Okay, no, all that I want to say is that if you kind of, you know, take intuitively, right, take an execution graph, like in the store buffer example, make it a bit more interesting by adding some extra writes, like I was trying to explain to Raghavan. Okay, if you had more writes, the point I was trying to drive home is that a modification order there, right, between, like, if there is MO like this and coming back, okay, from process 1 to process 2, that need not directly translate to strictly increasing timestamps for X between the two processes. That is all I was trying to say, basically. And if you think about it, it's perfectly fine, you know, because when do these timestamps matter? These timestamps matter when you're trying to read from there later. So this is just one possibility, right? That even if there was a read in process 1, let's say after the first write of X, process 1 need not have read from the write of process 2. It could have read from its own write. That is what is being captured when I choose a timestamp for process 2, which was smaller than what was chosen by process 1. Now, if you were insistent on reading from this particular write, you could have chosen a higher timestamp here. So there are, you know, several cases to consider if you want to talk about the equivalence, right? Because in some sense, if when you talk about an execution graph, again, it's a fixed execution. So maybe if you want to respect that, you'll have to choose the timestamps in a certain order, which will respect your release acquired consistency. But then, you know, that is just one possible way to choose the timestamps.
Okay. Thanks, Krishna. Thanks for your patience. So, yeah.
No. I think I'm learning along with all of you guys. So no need to thank you.
So I'm done. Yeah. Thanks.
Yeah. So yes, I believe we'll end this one here, and I mean, we must thank Krishna for a wonderful talk, lecture, whatever we can say. And for patiently answering all this, you know, even though it's getting late.
My pleasure. So honestly, you know, if I'm being honest, so I gave the same talk a couple of days back, okay, in this conference called A+. It was a keynote. So there, you know, I was like racing to finish in 1 hour with questions at the end. So compare that such a leisurely manner, today, like take every slide one at a time. So, when I started, I was in that mode. And, now I like this mode better, if I'm being honest. It's relaxed somehow.
Yeah.
Of course, relaxed memory, the talk should be relaxed.
Of course, yeah. So nice of you. Okay, so and also, yeah, thanks to you for agreeing to do the second part sometime. I hope we'll be able to schedule it in January, or if not in January, then sometime, so that you can learn about the results that you wanted to talk about. If there are no further questions, we would like to, we must thank Krishna and.
You already thanked me like twice.
Oh, okay.
Thanks, Krishna.
Yeah. Okay. And we would like to end here, and we will do a second part of this sometime whenever it works out for us.
Yeah, ideally in Jan, if there's nothing else, and if Krishna is okay with it, we can have it next
Yeah,
week.
I would also like to do it in Jan, just that, right now, I'm not 100% sure, but yeah, hopefully.
Sure.
Sure. Okay. So I'll stop the recording and.